A little bit of chemistry, which I sort of didn't know. I probably should have known this before. Generally, antagonists are bigger and bulkier than agonists. I sort of had seen that in a lot of pictures, but I didn't understand why. Part of the reason is I think that, as the text describes, essentially competitive agonists tend to be bulky and lipophilic compared to the agonists, don't always share really tight structural similarities. In order to explain this exception to the concept of stereocomplementarity, again, antagonists, if they're going to bind at the same receptor, you'd think they'd be really identifiable, similar core kind of structure. But I'll show you a couple of pictures and you'll say, well, yeah, I guess what you're saying is true. They're bigger and they essentially allow for a little more hydrophobic binding so that they can essentially occupy the site with a higher degree of affinity than agonists. So I think what this quote is all about is that agonists tend to look a lot like the ligand structurally, probably a little on the smaller side. Antagonists will look like the structure of the ligand, but it's a little more disguised, a little bigger, so that they can have some additional hydrophobic binding so that they can prevent the endogenous ligand, they can prevent other ligands from binding. Question?
So going back to the allosteric modulation, an antagonist can bind to an allosteric region on the receptor that would decrease binding at the binding site, but could it also, could like you have a competitive agonist that binds at the allosteric site that increases the binding affinity at the binding site?
We'll go back to the allosteric binding in just a second. So far what we had really talked about in the slide previously, it was not allosteric binding, it was really direct binding with the receptor. The agonist converts virtually all of them to the active site. The inverse agonist, full inverse agonist, converts virtually all of them to the inactive site. The competitive antagonist binds but doesn't change that balance. Allosteric modulation will come in just a second. Okay? But just to sort of show you some of the chemistry, this is from the textbook again. If epinephrine is the agonist, epinephrine is one of the molecules that's released with the renal discharge. You get really excited, you have norepinephrine, epinephrine release. That's the agonist. Ephedrine and amphetamine, not exactly direct agonists, but they work through a similar mechanism. They're structurally like the ephedrine. Some of the blockers, whether an alpha blocker, prazosin, or a beta blocker, atenolol, they're bigger and bulkier. And I think that allows them, as the text says, that allows them to have some additional hydrophobic binding that might allow them to prevent the agonist from getting there. So we've talked about the two-state model, we talked about agonists, partial agonist, inverse agonist, partial inverse agonist, and antagonist. Now we'll talk a little bit about allosterics. Again, allosteric modulation, I think I've said this before, a lot of drugs will work directly at the receptor, and we just talked about agonists, full agonists, we're talking about partial agonists, we're talking about partial inverse agonists, we talk about full inverse agonists, we talk about antagonists. Those are all sort of directly at that receptor where the ligand is working. Sometimes that's too hard a hammer to use. So you want to use something more nuanced. And so allosteric receptor interactions are probably sometimes more useful. And there are ways, however, to intercede in a receptor function that allow for more controlled and selective tuning of the drug action on the receptor. Allosteric modulators, as I said before, bind to distinct sites from the receptor's active site, resulting in conformational changes. Allosteric receptors can be receptors too, though. It's not that allosteric binding is not a receptor process, but understand it's apart from the normal endogenous ligand process. So there's a receptor system modulating a receptor system. That's what the allosteric modulation is. And you can have all of those same kind of changes with allosteric. You can have an agonist, a partial agonist, a full agonist, an antagonist, binding and interacting with an allosteric site too. And that would do the modulation of that normal receptor, but it wouldn't relate to the actual transduction that receptor produces. If I can make that clear. So you can have levels of allosteric modulation too. I'll show you an example of that in just a second. How are we doing? 9:44. We have 6 minutes. Okay, what are we going to get into? So a little more on allosteric modulators. Agonists, they enhance the affinity. I think I just said this. Oh, no, I didn't say that. Anyway, allosteric agonists, enhance the affinity or action of the ligand when it, while having no effect on their own. They facilitate the ligand action at the endogenous receptor. And allosteric antagonists essentially don't change that, and then allosteric inverse agonists reduce the affinity of that agonist. And we'll give you a couple of examples of that. Probably not, though. This is another cartoon. This is from your text. I don't like this cartoon as much, but since it's from the text, I threw it up there. This is, again, another cartoon, if you will, of the GABA-A benzodiazepine receptor complex. It's a polypeptide stuck in the membrane. On the outside, you have a GABA receptor. There's a GABA. GABA is the little hat head there, the little triangle kind of thing. That's going to fit in the receptor. That's going to open the chloride channel. Chloride ions are going to come in. We have next to that, doesn't have to be exactly next to that, is a benzodiazepine site. That looks like a little very short screw. It sort of fits on the top there. When that allosteric site is activated, that facilitates the GABA action. So benzodiazepines are agonists at the benzodiazepine site, at the benzodiazepine receptor, but the benzodiazepine receptor is an allosteric modulator of the GABA-A receptor. So you can have agonists and antagonists and partial agonists at an allosteric site as well. We're not going to go through all the ramifications, but basically, in the normal course of events, chloride is coming into that cell because GABA is always activating that receptor. There's a tonic activity of that receptor to open the chloride channel. If you give a benzodiazepine, that GABA effect works more dramatically than it did before. But it doesn't work through the GABA receptor, it works through the benzodiazepine receptor, which facilitates the binding of GABA to its receptor. A similar story happens with barbiturates like phenobarbital, amylbarbital. They don't work through the benzodiazepine receptor, but they have a different receptor for modulating this GABA receptor. Those are allosteric modulations. And again, this is another cartoon. Again, chloride channels in the heart and soul of this business. The GABA receptors on the tip there. There's a barbiturate site, in this case located near the channel. There's a benzodiazepine site. Activating the benzodiazepine and barbiturate sites don't do anything directly to the chloride channel, but they facilitate the effects of GABA to open that chloride channel. They're agonists at the benzodiazepine site or agonists at the barbiturate site, which act to facilitate, in an allosterically positive way, GABA-mediated opening of the chloride channel. And there are a lot more examples. This is just one example. I'm going to introduce a concept, and then we're going to take a break. I got to introduce the concept, I think. 3 minutes, yep. So we're going to do some quantitation. I'm going to demethylate this a little bit for you. I've seen lectures on this. I've given lectures on this. I think we can talk a lot about how to quantify drug receptor interactions. We can talk about numbers like efficacy numbers. We can talk about spare receptor numbers and do complicated math things. But the only math I'm going to have you be really responsible for is understanding what a KD is, a dissociation constant, why that matters. Because that's a number that you'll see in primary literature. You'll see it in primary pharmacy literature, you'll see it in primary basic pharmacy literature all the time. And what's one word that I have said repeatedly when we talked about agonists, antagonists, inverse agonists, the normal ligand? I've used the term affinity. Affinity is simply how effectively this chemical, whether it's the normal ligand or whether it's an agonist, whether it's an antagonist, an inverse agonist, a partial agonist, affinity is a measure of how effectively does this thing bind to that receptor. What's the concentration required for that drug to occupy half of the receptors? That's the definition of what's called a KD. KD, K sub D, is a dissociation constant. We'll get into this a little bit more, but we'll really pick it up on Wednesday. Is the measure of what's the concentration of the drug required for half of the receptors for that system to be bound by that drug. And so KD is our measure of affinity. And essentially, the lower the KD, if we're talking, the KD figures are usually in the micromolar or maybe in the nanomolar range, kind of thing for most drugs. If something has a lower KD, that means it has a higher affinity for the receptor, because a lower KD means the concentration of this drug to bind 50% of those receptors is lower than some other drug. 10 micromolar KD is a drug that has more affinity for the receptor than something that has 100 micromolar KD. Because 100 micromolar is the concentration required to activate half the receptors. The smaller that number is, the more that drug will, the more specifically or selectively that drug will bind to that receptor. So we're going to talk about this in much more detail. That's sort of the affinity argument. We touched on that now. We just parked that concept, and we'll talk about KD a lot. Now, we also said the drug's going to have, I'm going to use a term called intrinsic activity. I'll just define these terms, and then we'll take our break. Intrinsic activity is really, after the drug binds to the receptor, what does it do? Does it push it to the active state of the receptor? That would be an agonist, and that would have positive intrinsic activity. Does it push it to the other side, the inactive state? That's an inverse agonist. That's going to have negative intrinsic activity. And full agonists and full antagonists are given values of 1 for full agonist and -1 for full antagonist, or excuse me, full inverse agonist. If the drug binds to the receptor and doesn't change the balance, we called that an antagonist. It'll bind to the receptor. It has affinity for the receptor, but it's not going to change whether it's inactive or inactive in the conformation. That's an antagonist. By definition, that has an intrinsic activity of 0. And then partial agonists are between 0 and +1 for the partial agonists. Partial inverse agonists are between 0 and -1, because they move it to the inactive state, but not to the extent of the full inverse agonist. That's intrinsic activity. We'll touch on that. Receptor reserve, I have to introduce this. Do I have a minute left? Oh, I'm over. Receptor reserve is a situation where it's also called spare receptors. What an awful misnomer that is. Receptor reserve, in a nutshell, because we'll come back to this, is a situation where maybe the number of receptors that you activate is not the limiting factor. Maybe the limiting factor is the amount of cyclic A you can generate. If cyclic A that you generate is going to be the limiting factor, and you activate a bunch of receptors, if you run out of cyclic A, you can activate more receptors, but if cyclic A is responsible for that transduction process and you're all gone, it's all used up, it doesn't matter if you activate more receptors, you don't get a bigger response. That's a misnomer called spare receptors. We'll talk about that. And then the last thing, we're going to put everything together and say the effect of the drug, the actual efficacy when you give the drug, is going to be a combination of its affinity, its ability to bind the receptor on a drug-receptor kind of an interaction. It's going to be related to the efficacy, the intrinsic activity of that drug, that is the ability of that drug to either activate, move toward the active conformation, or move to the inactive conformation. And it'll be a product of whatever receptor reserve might be out there. And we'll come back and we'll pick up with those on Wednesday. And sorry I went over a little long.